So next up is Thomas Dumitrescu.
Okay, great. Thanks a lot for having me and for giving me the opportunity to talk about this work. So the title of my talk is Anomalies, RG Flows, and the a-Theorem in 6 dimensions. Everything I'm going to talk about is based on work together with Clay Cordova and Kenneth Trilligator. There's a paper that came out in June that will be the basis for most of the talk, and there's some unpublished work that will hopefully appear soon. The title includes 6D, and our results are in 6 dimensions, but to have a little bit more time, I'm going to start building the story up from the ground up and review more or less what's known in lower dimensions, and then we'll see what we can say in 6 dimensions. So sort of our post-Wilsonian point of view on quantum field theory is based on the very general idea that quantum field theories are best understood as renormalization group trajectories between scale-invariant fixed points. And in many nice examples, it turns out that those scale-invariant fixed points are also conformally invariant. So the canonical picture that we sort of have in our heads when we think of what you might call UV-complete quantum field theory is a pair of fixed points where you have a conformal field theory in the UV, and then there's some non-trivial RG trajectory. How exactly that trajectory gets triggered need not concern us right now. I'll say more about it later in very specific contexts. And then, as you go from high to low energies in the deep infrared, you'll end up with another conformal field theory, which will generally be different than the one you started with. Okay, so as I said, I'll say a few words later about what kind of flows we could contemplate, but of course the simplest example that's very familiar is that you can just start with a CFT in the UV and add a relevant operator, local operator to the Lagrangian, and that triggers such a flow. But there are other things we could do. Now, a very basic intuition that's kind of hardwired into this picture is the idea that the effective number of degrees of freedom that we probe as we move along this flow from the UV towards the IR is decreasing. And that goes under various names. It goes under coarse graining or integrating out or whatever you want to call it. But there's some notion that there are more degrees of freedom that you see at short distances than you can access at long distances. Okay, this is a beautiful picture. It has a long history. In order to make this picture perfectly precise and quantitative, we need to do a little bit more work. And I'm going to start telling the story in 2 dimensions, where this picture was essentially completely worked out in the 1980s, where it is associated with the names of Zamolodchikov and Kolchinsky and others. Okay, so I'm going to start by talking about a unitary Poincare invariant 2D quantum field theory. And unitarity will play a crucial role throughout the talk, so many things can go wrong if we drop that requirement, and the same is true for Poincare invariants, actually. So I'm going to assume that Poincare invariance implies the existence of a conserved and symmetric stress tensor. I'm going to take that as part of what I mean when I have a quantum field theory with that symmetry rather than some other quantum mechanical system. Great, so these 2 conditions, the fact that the stress tensor is symmetric and conserved, are just a restatement of Poincare symmetry. Good.
It's a slightly stronger state. There's some locale.
Yeah. That's what I mean. That's what I meant when I said this is what I'm going to take to be my definition of local quantum field theory, as opposed to any other quantum mechanical theory with Poincare symmetry on its Hilbert space, of which there are many. Great. So the stress tensor is this nice universal object in the theory, and since we're trying to make precise a very basic and universal notion, it's perhaps fitting that we should talk about it. In 2 dimensions, as I said, this picture basically can be made precise by studying the 2-point function of the stress tensor. So let me work in Euclidean signature and use holomorphic and anti-holomorphic coordinates. And I'm going to very briefly review the argument of Polchinski and Zamolodchikov. And in order to do that, I'm going to have to look at various components of the stress tensor 2-point function. So for example, I can look at the 2-point function of the chiral spin 2 parts, and I'm always going to include some prefactors in order to absorb the scale and spin dependence of these correlation functions. So I'm defining Lorentz invariant quantities here. And for now, I'm not working in a conformal field theory. In a conformal field theory, this would be a simple power law that would then be cancelled by this prefactor, so I'll just get some number. But for now, I'm assuming that I'm in a general massive theory. So here I'll get a Lorentz invariant function of the dimensionless combination x squared, m squared. X squared is just the radial distance, and m squared is some mass scale in the theory, which we typically think of as some sort of crossover scale along the RG, where you transition from UV to IR behavior. But of course, in more complicated flows, you could have many different mass scales, and this is one of them, just in there for dimensional reasons. Okay, so I'm also going to look at other components of the stress tensor 2-point function. For example, here I'm including one with a trace of t. Okay, and again I'm going to multiply in such a way that I can make a Lorentz scalar combination, and then there's a third combination that I need, which is the actual 2-point function of the traces. Okay, so as I said, in holomorphic coordinates, this thing is just the trace of t. Good. And another thing that we can immediately say using unitarity is that because this is a 2-point function of the same operator at separated points, it has to necessarily be positive definite. So in a unitary theory, f has to be greater than or equal to 0, and the equality is only possible if the trace of the stress tensor is actually 0 as an operator. Okay, good. So now there's a very simple bit of algebra that I'm not going to do out in detail. I'm going to write what the answer is, but by simply using this differential equation inside the correlation functions, so just by imposing the Ward identity on these correlation functions, there's a non-trivial differential constraint on the functions d, e, and f. Okay, so let me write it over here. Is it okay if I?
Yep.
So the constraint is that if I look at the radial derivative, remember that x is the radial distance, of the following combination of d, e, and f, and there are going to be some numerical coefficients here that are chosen judiciously in order to make the relation come out. So this radial derivative is equal to minus 12 times f itself. Okay? So what is the interpretation of this formula? Well, on the left-hand side, we have a function of the radius. So we can track that function along r from short to long distances, and tracking that function from short to long distances is interpreted as traversing the RG flow. So at very short distances, that function computes something about the UV. At long distances, it should compute something about the IR. And on the right-hand side, we have one particular 2-point function of the stress tensor, and in fact, it's the 2-point function of the traces, and that's important. So as I said here, unitarity implies that this is positive definite. And because of this crucial minus sign, it means that this combination of d, e, and f is actually decreasing as I go to large x. So as I approach the infrared, that combination is decreasing.
Is it positive or negative?
Excuse me?
There's a minus sign.
He's saying F.
Oh, I'm sorry,
is
F is positive.
So
F is positive, this thing is negative. Thank you. So let me define the quantity in brackets here to be a new function, c of x squared m squared. And so that statement is the statement that the function c of x squared is monotonically decreasing. Okay. We can, in fact, say even more. At a scale invariant fixed point of the renormalization group, it is necessarily the case that the stress tensor scales with its canonical dimension, which is 2. Okay? And then by construction, the scale variation of these combinations here on the left-hand side have to be trivial. So at a scale invariant fixed point, the left-hand side has to vanish. And that means that the right-hand side also has to vanish. But I said before that if the function f vanishes, it means that the 2-point function of traces vanishes. And that means that the trace is 0 as an operator. Okay, so this is basically Polchinski's argument for why scale invariance at fixed points implies conformal invariance in a unitary Poincare invariant field theory. Great.
Were you going to say something about how you get this relation?
Well, as I said, this relation is 2 or 3 lines of algebra that just follow from these definitions and the conservation equation.
That's all it goes.
That's all. It's totally elementary. Yeah. Good. And so at a scale invariant fixed point, this thing is 0. Therefore, c is a constant. And at a fixed point, that constant c is nothing but the Virasoro central charge. So at a fixed point, c squared m squared is actually c Virasoro, and it's a constant.
So this relation was derived by Zamolodchikov, or?
This relation was first written down by Zamolodchikov in a slightly different form, and then sort of streamlined by Polchinski. And the argument in particular that it implies conformal invariance without putting that in from the beginning is due to Polchinski. Okay, so the last comment I want to make is that since this Virasoro central charge is itself given by a 2-point function of tzz at separated points, it is also necessarily positive in a unitary theory. And that sort of completes the picture in 2 dimensions. So let me make here maybe a little summary of the kind of things that hold in unitary Poincare invariant 2D theories, 3D field theories. So the first thing is that scale invariance and scale invariant fixed points are in fact CFTs. That's a pretty powerful statement. The second statement is that there exists a function of the coordinates, which I call c of x squared m squared, this function here, that is monotonically decreasing from UV to IR. Okay? And
Did you also say that you had shown that D was positive? I didn't catch that.
Oh, D is positive because, again, it is the 2-point function of the same component of the stress tensor at separated points.
But that guy is a complex number. Does this matter?
This is a brain fake in Euclidean signature. If you think about it in
Okay.
Lorentzian signature, it's t++ with t++. It's just totally real.
But
In
then-
Euclidean signature, you have to both complex conjugate and take the time reversal, and that those 2 effects cancel each other. Yeah. I mean, from many different points of view, that C has to be positive, but
Yes.
but this is one of them. Okay, and the third point was that the C function actually approaches C Virasoro in the UV and in the IR, where I have here defined C Virasoro via the stress tensor 2-point function at separated points. And the fourth point, which is the one that you just asked about, is that C Virasoro, or alternatively capital C, is actually non-negative in a unitary theory. And again, the equality is only possible if the operator is actually 0, and then in this case we're talking about that operator. So that means that C Virasoro is only 0 if the stress tensor is 0 as an operator, and the theory has no local degrees of freedom whatsoever. Okay? And again, all of this follows from simple manipulations of the two-point function with the stress tensor plus ward identities.
I think in the homological you can convert this derivative with respect to mu, the normalization K, and the beta function.
Now, you can do that. That's sort of a development of the story that departs a little bit from this very general non-perturbative argument, and that requires you to talk about perturbations, sort of small perturbations around the UV fixed point. Once you put in the once you put in the beta functions and the couplings and so forth, you're sort of committing to some sort of conformal perturbation theory description of the flow, and that's a fine thing to do in the vicinity of this point, but it's honestly not clear to what extent this description is valid or kind of non-perturbatively valid along the flow. So this part of the story didn't require any kind of perturbative
Yeah, but
thinking.
I didn't say anything about what happens in the normalization group flow.
I
Just saying that
I have used a notion of renormalization group flow where instead of introducing some arbitrary scale, which always sort of throws in an element of arbitrariness into the story, I've substituted instead for this radial function. So I'm going to use just distance in correlation functions as a proxy for a renormalization scale. This is the thing that I can make completely precise. The other thing works extremely well in conformal perturbation theory, but its non-perturbative meaning, I think, is not fully understood. So I will not try to write any formulas involving beta functions and things like that. Good. Now, and it's clear how this makes precise this simple picture. We now have a function C, has a definite positive value here, it has a definite value here, which may be positive or 0, depending on whether the theory in the infrared is gapped or not. There's a monotonically decreasing function of distance that interpolates between them, and so this is kind of the quantitative picture associated with the RG intuition. Okay, great. Now, in 2D, we get a lot of mileage out of this. And as I move up to higher dimensions, I'll be able to say less and less analogs of items on this list. So let me just distill one consequence of these 4 points, which is one thing that I'll keep referring to in higher dimensions. So one version of this degree of freedom thinning out along the RG flow is simply the statement that CUV minus CIR, or delta C, is strictly positive. This is a trivial consequence of what is written there, but it is weaker. There we also had a monotonically decreasing interpolating function. So this is the version of what's sometimes called the C-theorem that I will most often try to make contact with in higher dimensions. There have also been attempts to make contacts with some of the stronger statements in higher dimensions, but I won't have much to say about them, especially not in 6 dimensions. This is sometimes called the weak version of the C-theorem. Okay, great. So as I said, the goal for the remainder of the talk is to try to discuss the status of analogous results in higher dimensions, and especially 6 dimensions, where we have some new results. But sort of in order to set the stage, and also in order to introduce some of the techniques that I will rely on in 6 dimensions, I'll first pass through 4 dimensions, which is sort of a pretty non-trivial intermediate step that took a pretty long time to get straight. And the reason why I'm saying 2, 4, and 6 rather than 2, 3, 4, 5, and 6 is because there's a sort of parallel story in those even dimensions, and that story depends on the observation that one of the many different interpretations for the Virasoro central charge in 2 dimensions is as a Weil anomaly coefficient. And those Weil anomalies only exist in even dimensions. There's also a beautiful story in odd dimensions, which has been the subject of much recent work, but I won't have time to talk about it today. Okay, so let me say something about the Weil anomaly in 2 dimensions, and then we'll jump to higher dimensions. So the way that the Weil anomaly is commonly introduced is by coupling the field theory to a non-dynamical background metric d mu nu, and then studying the trace of the stress tensor, the one-point function of the trace of the stress tensor in the presence of this background metric. And whereas this operator is identically 0 in flat space at separated points, etc., it has a non-trivial one-point function in curved space that is proportional to the Virasoro central charge and the Ricci scalar R. And I just remind you for future comparisons that the Ricci scalar in 2 dimension has the property that if you integrate it over a 2-manifold, it gives the Euler characteristic. So R is simultaneously the 2-dimensional Euler density. Okay? Now, this equation, of course, doesn't imply that conformal symmetry is broken. It certainly doesn't imply that conformal symmetry is violated in correlation functions at separated points in flat space. However, it does imply that even when you study the theory in flat space without the background metric turns on, there are certain conformal symmetry violating contact terms in correlation functions that you would otherwise have said are 0. And in particular, this equation means that if you look at the 2-point function of traces in flat space, so where d is just the product or delta, then this is identically 0 at separated points, which is necessary for conformal symmetry, but it's a non-trivial contact term proportional to the Virasoro central charge. Okay, so the anomaly is a statement that while the trace is a 0 as an operator, it doesn't quite decouple at coincident points. And this can be made sort of more visible or more palatable by coupling the system to a background metric, and the background metric then picks up this contact term and converts it into this Ricci scalar on the right hand side. Good. So this is one of the millions of ways of saying what the Virasoro central charge does in 2 dimensions, but this story has a nice generalization to all even-dimensional conformal field theories, because all of them have Weil anomalies. Okay, so the analogous equation in any even dimension 2n is that the anomalous trace of the stress tensor in a background metric involves a number of different terms constructed out of curvatures. There's one term, which I will write with coefficient little a, that is proportional to the d-dimensional Euler density. And recall that the Euler density is some polynomial in the curvature. It's some, d over 2 degree polynomial in the curvature, and it has the property that if you integrate it over a d manifold, you get the Euler density. Okay, and then it can have a number of different other curvature invariants on the right-hand side, and these are typically denoted with coefficient c, and there can be one or several of them depending on the space-time dimension. So let me denote the number of c's by n sub c. N sub c is not the number of colors. And the c anomalies multiply some curvature invariance capital I that I will not say much about or write down explicitly, except to say that they are constructed out of the Weil tensor. So in fact, they are total Weil invariants. If you do a Weil transformation on these guys, they're Weil scalars. You can include a factor of the metric in front. The Euler density is different in this way because it is not actually totally Weil invariant. Under a Weil transformation, it shifts by a total derivative. Okay? So in every even dimension, there's a special term in the Weil anomaly, which is the term proportional to the Euler density that I will call little a. And there's a possibility of having one or none or several of these i's. Just to orient you, let me write the number of i's as a function of dimension. So in 2 dimensions, you might think there's one I, but that's misleading. In 2 dimensions, there's an unfortunate naming clash because R is actually the 2-dimensional Euler density. So in 2 dimensions, what is called A here is called C here. And in fact, there are no i's. Okay? So in 2 dimensions, the number of i's is 0. And in 4 dimensions, it turns out that there's one I, and therefore one C anomaly. And in 6 dimensions, which will be the other case we'll be interested in, it turns out there are 3 i's. Okay? And the number of i's proliferates rapidly because the number of Weil invariants of dimension D that I can write here proliferates rapidly as I go up in dimension. Good.
I mean, these are just more or less all the different inequivalent ways of contracting the that appropriate number of Weil tensors in each dimension?
It's a little more complicated than that because, for example, you could also have things with Weil covariant derivatives acting on the Weil tensor. So, for example, in 6D, you'll have 2 different terms that kind of look like Weil cubed. There are 2 inequivalent contractions of Weil cubed, but there's also one term that looks roughly like Weil d squared Weil, Weil d squared Weil, where this script d is some sort of covariant Laplacian, conformally covariant Laplacian. So they just need to be conformally invariant. But they're naturally constructed out of the Weil tensor and these covariant derivatives. Now, the Weil anomalies, just like in 2 dimensions, are fairly robust observables of any CFT. By fairly robust, I mean, they're anomalies, so they have all sorts of wonderful properties and satisfy non-renormalization theorems, and it can be accessed more directly than many other features of the theory. But I do want to make a distinction between the Weil anomalies and the more conventional 't Hooft type anomalies for flavor symmetries, because the 't Hooft anomalies have the nice feature that they can really be tracked along non-trivial RG flows, and they satisfy matching conditions along non-trivial RG flows. Whereas the Weil anomalies, even though they're perfectly well defined at the conformal point, sort of lose their meaning if I deform the theory away from conformality by, say, adding a relevant operator and triggering an RG flow. So, they're perfectly meaningful observables if you have the capacity of studying the CFT directly. If you want to embed the CFT in some bigger system that you know how to control, but that's not conformal, then it's going to be quite difficult to extract these anomalies in this kind of non-conformal description, because you need to fine-tune yourself to the conformal part. And so this is, morally speaking, why they are harder to compute. Good. So there are many possible ways you might consider generalizing the C-theorem in 2 dimensions, but John Cardy proposed a long time ago in 1988 that the right thing that one should look at in higher even dimensions is this A-type Weil anomaly. And she already has it's singled out because it's sort of unique compared to the other C's. And so Cardy basically proposed that in all even D, for unitary theories and RD flows, you have an inequality of this type. So this is what's referred to as an a-Theorem, or the a-Theorem, or whatever you want to call it. So this is Cardy's conjecture, and he made that conjecture based on a few weakly coupled examples and some circumstantial evidence in 88. He did not try to define a function such as C that monotonically interpolates between the UV and IR values of A. So this is sort of the weak, quote-unquote, weak statement of the A-Theorem. And because it involves Weil anomaly coefficients, this conjecture only makes sense in even D. So again, question about what happens in odd D, and there's a nice story there. but it's sort of outside of the line of the dot. And in 4 dimensions, the conjecture was first analyzed extensively in conformal perturbation theory by Hugh Osborne and collaborators. And in a sense, they actually managed to prove it in perturbation theory. So near a conformal fixed point, if you have either a very short RG flow to a nearby fixed point, or you just are interested in the variation of A near the fixed point, they managed to come up with a natural quantity that is equal to A at the fixed point and is monotonically decreasing away from it. This is early 90s. This is kind of an amazing result, but I don't think it was very widely known or appreciated. And even though it's completely correct, it does have the drawback that it's perturbative. So the non-perturbative understanding of this conjecture really only happened sort of in complete generality in 2011 and subsequently from the work of Komargatsky and Schwimmer, but there's a sort of long history in between of people exploring the 4D and testing the 4D a-Theorem, including many nice pieces of evidence that were gathered in supersymmetric theory. So that's something I'll talk about in a little bit. But let me first stick to the bosonic story and say what is now. So let me first say a few words about why it's so much harder to say anything sensible about A in 4 dimensions than C in 2 dimensions. Okay. So as opposed to C in 2 dimensions, which was in a 2-point function of stress tensors, A first appears in a 3-point function in 4 dimensions. Now a 3-point function isn't that bad. A 3-point function is the same type of object that we study when we study at Hooft anomalies. It's the same type of object. In the conformal field theory, it's fixed by a few numbers. It's not a complicated function. The problem with the 3-point function is that it doesn't have any obvious positivity properties. So it's not easy to figure out how to impose the constraints of unitarity. In fact, for a long time, it wasn't even obvious why the A anomaly should be positive. One thing that Carty didn't conjecture explicitly, but that you might want to be true, is that A is in fact positive for a unitary conformal field theory. Okay, and it turns out that there's a nice argument that A is positive, but it's a little bit roundabout. So Hoffman and Maldacena gave a very nice physical argument that A had to be positive based on the following physical picture. So they looked at the T 3-point function, which is some function that depends on A and also the C anomaly coefficient. In fact, it has 2 different structures. One is governed by A, one is governed by C. And they interpreted this 3-point function as the expectation value of the stress tensor in some state psi, where the state psi is itself created by acting with the stress tensor on the vacuum of the theory. And then they integrated that stress tensor 1-point function over asymptotic null infinity to get what you might call the energy flux through asymptotic infinity. And by demanding, based on sort of basic physical requirements, that this energy flux is positive, they were able to prove an inequality on the ratio of A to C. Okay, so they proved this inequality for A over C based on the positivity of the energy flux. So this is Hoffman and Maldacena. And the good thing about C is that even though it doesn't play a role in this Carty conjecture, it is in fact the 2-point function coefficient of the stress tensor. So therefore it is trivially positive, just like in 2 dimensions. And together those 2 inequalities imply that A is positive. So already the proof that A is positive is not trivial, but we have a proof. There's a nice argument, and there have been various refinements of this proof over the years. However, even so, we don't quite know how to exploit the properties of the 3-point function in order to give a proof that A is monotonically decreasing, or even just that delta A is positive. And the thing that sort of comes to the rescue in 4 dimensions is the fact that the A anomaly doesn't just appear in the 3-point function, it actually also appears in the 4-point function. The Ward identities imply that the conformal anomalies don't just appear at the lowest order where they arise, they sort of propagate up to high point function. And the 4-point function has a chance of having good positivity properties. However, the 4-point function of stress tensors is a daunting object. It's technically extremely challenging to analyze this object, even in a CFT. In fact, it's sort of an open technical problem to try and get a good handle on this object, even directly in a CFT. The reason is that even in a CFT, this is a non-trivial function of conformal cross ratios, on which then you have to impose all the Ward identities of conservation and so forth. Away from the critical point, it's practically helpless. And so the key physical insight that Komorowski and Schwimmer applied and that led to substantial progress was a kind of physics-motivated trick for how to single out precisely the right components of the stress tensor 4-point function without actually trying to brutalize it. And this is what I'll call the dilettante trick. So their physical argument was based on the following scenario. Consider a conformal field theory that also has a moduli space of vacua. Such theories might not be particularly common, but they abound in supersymmetric examples. For example, 4-dimensional n equals to 4 super Young-Wills has a moduli space of vacua. Now, because some fields get expectation values on the moduli space of vacua, conformal symmetry is spontaneously broken. And that means that there is a Nambu-Goldstone boson that arises because of this spontaneous symmetry breaking. Okay, so we have a picture that looks a little bit like that. We have some CFT here at the origin. This is the moduli space of vacua. And I'm looking at some point here where some fields develop a VAV. Okay. If I study correlation functions in that vacuum, they will have a non-trivial scale dependence. They will not be the simple scale invariant functions that you see in the CFT. So in that sense, there's a non-trivial RG flow kind of from the UV theory, which is the theory at the origin, to the infrared theory. Correlation functions are non-trivial functions of position, and there is a crossover scale that's set by the VEV at which you integrate out all the stuff that became massive when you went onto the moduli space. Okay, and the key idea was to use the fact that there is a Nambu-Goldstone boson, script phi, associated with conformal symmetry breaking, and this, motivated by string theory, we call it the dilettante. And the Goldstone theorem says that the dilettante is a free field in the deep infrared. There has to be a nice single particle pole in the various correlation functions. And then, once you move up to slightly higher energy, the dilettante can very weakly interact with itself through derivative interactions. So it's really a Goldstone boson. And it sort of singles out a nice weakly coupled subsector of the problem. And moreover, these self-interactions of the dilettante are constrained by conformal symmetry. Right? This is a very standard fact about spontaneous symmetry breaking. Even if the vacuum breaks the symmetry spontaneously, the Goldstone interactions are still constrained by it. So typically we say that the symmetry is realized non-linearly, but it's still present. Good, so I said that at very low energies, the Goldstone field is just free, so there's a nice kinetic term for phi. And then it turns out that the leading non-trivial dilettante self-interaction that you can write, even just consistent with scale invariance for starters, looks like that. So it's basically like a kinetic term squared divided by phi to the 4th. The division by phi to the 4th is clearly necessary just based on scale invariance. I want this thing to scale with dimension 4, phi has dimension 1, so the numerator will have dimension 8, and therefore I need to divide by phi to the 4th. And dividing by phi to the 4th is what makes it clear that we're in the spontaneously broken phase. So phi will get a VEV, and that will break the symmetry spontaneously. Good, so it's clear that this term is dilatation invariant. In fact, yes?
Usually they say Goldstone boson is the only massive particle, and then it has an action by itself decoupled from the rest. But here in the infrared, you have all these conformal field theory. Why is it decoupled?
Very good. In fact, it does not decouple. You basically have a situation where in the infrared, let me say that the infrared theory is the Goldstone plus potentially some CFT that you are left over with. For example, imagine taking n equals to 4 and just partially moving onto the moduli space, like pulling one brane off of a stack of parallel D3 branes or something like that. Then what you have is that in the deep, deep infrared, the dilaton and the IR CFT decouple. That's necessary by Goldstone's theorem. But just like you can have higher derivative self interactions of the dilaton, you can also have higher derivative interactions between the dilaton and the remaining IR degrees of freedom. So there can be also other local operators here in this effective action that include some derivatives of phi, some power, times some CFT operator, divided by an appropriate power of phi. Now, it turns out, and you can argue this on general grounds, that this type of interaction always occurs at higher order than this term. So the leading interactions of the dilaton are only these self-interactions. If you also compute to higher order, then you might start seeing these kind of interactions with the CFT. And in fact, those are pretty difficult.
Higher order means higher derivative order?
Higher derivative order. Higher derivative order, exactly.
So the number of derivatives on the dilaton are...
Yeah, so this is strictly softer in low momentum than this. For example, if you want to study dilaton scattering amplitudes, this is going to be the leading non-trivial scattering amplitude, and this is going to be a correction to that amplitude that's suppressed in small momenta or small energies.
I'm a little confused because to take your n=4 example, there's not just a single real scalar, but they come in.
Yeah, that's right. You have the added complication of the fact that even on the moduli space now, because of supersymmetry, there are many decoupled fields. But it turns out that this argument is still correct. Like, there's only one scalar. There's only one direction at any point in the moduli space that is the dilaton. The other guys are Goldstone bosons for some other symmetry, namely the R symmetry.
And so there's no four derivative term coupling.
There's no
those
four
guys.
derivative terms. There will be higher derivative terms that couple them. But if you zoom in precisely on the dilaton, then it won't be affected by this. Yeah. No, that's a very important point because that's a potential place where the arguments that I'm going to review can break down. So people were very careful about checking this, especially in 4 dimensions. Good. So now, this is not typically a term that you might think is conformally invariant, but in fact it is. If you act on this term with a special conformal generator, you will find that, let me call this parentheses, ... If you act on this with a special conformal generator, what you will find is a total derivative of something plus another term that's proportional to box of phi. Okay? So the term proportional to box of phi vanishes on the dilaton equations of motion. And the total derivative term is phi. Once I integrate it, it gives a perfectly invariant term in the action. Okay? Now, the fact that this term is only invariant up to a total derivative is already suggestive. And in fact, this term is special. This term has an interpretation as a kind of Wess-Zumino term for the conformal, for the Weyl anomalies. And the claim of Komorgotsky and Schwimmer was that anomaly matching for the Weyl anomalies requires that this coefficient is precisely delta A, which is the mismatch between the A anomalies and the UV and then the IR. Okay? So delta A is UV minus the IR. And this is not easy to see from anything I've said so far. Once I review the analogous situation in 6 dimensions, I'll write it in a formalism that makes this much more manifest. But so far, just accept it as a fact, and also note that at least the fact that this term is not totally invariant, but only invariant up to a total derivatives, is a sort of typical feature of Wess-Zumino terms. Okay, good. So what this says is that anomaly matching for the Weyl anomalies in the spontaneously broken phase implies that the leading order self-interaction of the dilaton is completely fixed by delta A. Okay? And this is the key physical ingredient. Once you have that, it's actually pretty easy to prove that delta A is positive. The reason is that they're very general arguments that say that whenever you have a scalar field theory with some d phi to the fourth term like this, then its coefficient needs to be positive by unitary. For example, one way to see that is by studying this Lagrangian in a non-trivial phi background. So this is something that was emphasized by Adams and Arkani Hamed and others. And when you do that, you see that the fluctuations of phi propagate at a speed that is sensitive to this coefficient. So if you insist that they propagate with a speed that's smaller than the speed of light, as you would expect in a unitary causal theory, then you get a positivity bound on delta A. A more kind of mundane way of proving that delta A is positive involves writing the leading order scattering amplitude for dilitons, which is proportional to delta A, and then using a dispersion relation to relate it in some particular kinematical regime to the total cross-section, which is also manifestly positive. So these arguments are more or less standard. The key point is to get to this point and to declare that this coefficient is in fact delta A. Good. So this proves the a-theorem in 4D. This is essentially the argument by Kumargotsky and Schwimmer.
Wait, but
yeah.
Here you used the existence of a dilaton.
Ah, good. So this is why I initially called it the dilaton trick. So the other very nice thing they were able to argue for is that, in fact, you can extend this argument more or less without many technical differences to the case where the conformal symmetry is explicitly broken. Then the dilaton is not a physical propagating degree of freedom in the infrared, but you can introduce it as a background field that compensates whatever vile non-invariance your original theory has. And in fact, from a technical point of view, you can run the argument essentially without modification. You just need to say some words about how you couple this non-propagating dilaton to the original non-conformal theory in order to make it sort of spuriously conformal.
So if a theory is approximately conformal, is there also like a light dilaton, not exactly zero, like a single version?
Sure, sure. If this symmetry is very weakly broken, then the dilaton will have a very small mass.
That can be proven?
Yes, I think that follows easily from current algebra. The trace of the stress tensor would then be some operator that's non-zero but suppressed by a very small coefficient. And the trace of the stress tensor will essentially be responsible for giving the dilaton a mass. It's like having a small quark mass in the Pi Lagrange.
I think this is, you're talking about two different things. He's asking, in a theory where the conformal invariance is slightly
explicitly broken.
But explicitly
Yeah.
broken, is there going to be in the spectrum a light scalar?
If the conformal symmetry is broken extremely weakly, then I think the answer is probably yes.
I mean, we're not trying to, I mean, there doesn't have to be a light scalar in this. Well, I think it's not at all obvious that there should be a light scalar in the spectrum at all.
Well, there are.
Yeah,
We
exactly.
introduce a scale and there is nothing to compare that scale with anything. So what does it mean?
Well, I suspect that you need to say some words about what you mean by soft conformal symmetry breaking. So indeed, if you just have a free scalar and you add a mass, then clearly you will not get a nearly massless particle in the infrared. You need some small parameter, some small dimensionless parameter that suppresses.
Right.
That
Okay,
suppresses
so
the mass.
I
However,
just shifted the question. But yeah.
this is an interesting discussion. I deliberately glossed over it for two reasons. One is that there are some words that need to be said in 4 dimensions about the non-spontaneously broken case, and they said those words. But the other reason is that in 6 dimensions, for the class of RG flows that I will be interested in, there will in fact only be spontaneously broken ones. So that's why I'm just trying to confine the discussion for now to that case. But the other case is also very interesting, both in 4 and in 6 dimensions.
Are there any thoughts about how to extend this to a proof of a stronger a-theorem?
Good. So let me say I think, what is known about this in 4 dimensions. In 4 dimensions, the proof that they gave actually, in a sense, produces a monotonically decreasing function that interpolates between AUV and AIR. The reason is that they were basically able to show that delta A is proportional to an integrated dilaton cross-section. That proves the positivity of delta A. But that integral ran for over all energies in the scattering process. But if you cut off the integral at some intermediate scale, you actually get some running function of energy in the scattering process that is still monotonically decreasing because you have an integral of a positive density over some range of values that you shift. So in that sense, there is a monotonically decreasing function, but it's on a very kind of, well, at least superficially, it's quite different in spirit than this kind of correlation function of stress tensors at separated points, although it's indirectly related to a correlation function of stress tensors.
And is it obvious that that function exists when you don't actually have a dilaton, when you don't have a modulus space? Because now scattering amplitude at all energies is something which
they argued, I think, very convincingly that the answer is yes, but it's not a trivial argument. Yes.
So what
Has
does
been
it
proven.
mean?
Well, I think if you go through their arguments carefully, they do amount to a proof of this statement. Is it as kind of bulletproof as this argument in 2 dimensions? No. And we would like an argument like that also in 4 dimensions. However, such an argument would presumably entail studying the scale variation of 4-point functions of the stress tensor. The whole point of this dilaton trick was to sort of alert us to the precisely right combination of 4-point function coefficients. Now, nobody has actually been able to sort of write down the most general 4-point function of stress tensors and say, okay, this is the coefficient we should be focusing on. So that is sort of a long-standing goal, but it's technically very challenging. Good. So this proves the a-theorem in 4D, but let me just say that it doesn't actually improve the computability of A. Okay? It's still a very difficult problem, even after this argument, to compute A in any given strongly coupled theory. So this is the situation where supersymmetry helps a lot in 4 dimensions. Let me just briefly review that, and then I'll skip to 6 dimensions. When did I start, by the way?
You have about, let's see, 40 minutes left.
Yeah. Okay, so let's consider the situation in a 4D n=1 superconformal theory. There, we famously have a U1R symmetry that's included in the conformal algebra, and the stress tensor sits in a supermultiplet together with other conserved currents. So there's a supersymmetry current, S, and there's a current for the conserved R symmetry. So this is the R current. This is the multiplet of currents. Now, if you remember that A first appeared in the 3-point function of stress tensors, okay, you can now use supersymmetry warded entities to relate that 3-point function to 3-point functions of other operators in that multiplet. And it turns out that if you do that, you'll relate it to the correlation function of 3 J's, and also 1 J and 2 T's. I'm skipping the indices so that it doesn't take forever. I hope that doesn't cause confusion. Here I mean the stress tensor, not its trace. Okay, now these correlation functions are in fact encoding the 't-Hooft anomalies of the U1R symmetry. So this 3-point function encodes the trace R³ anomaly, and this 3-point function encodes the trace R anomaly. And supersymmetry provides a relation between this, and it's a linear relation, just like any warded entity. And therefore, there's a linear formula for the A anomaly in terms of these 't-Hooft anomaly coefficients. Okay. This is even clearer. So this discussion was at the level of 3-point functions that separated. This discussion is even cleaner if we now couple the theory to background fields, just as we did in the 2-dimensional case. And as we learned from Nadi Seiberg, it's always good to put the background fields in a supermultiplet as well. So if I want to turn on a background metric in order to study the Weil anomaly, I should also couple the supersymmetry current to a background gravitino, and I should couple the R symmetry current to a background R symmetry gauge field. And this is nothing but the supergravity multiplet, the n equals 1 supergravity multiplet. Except here, these are non-propagating, they're just background fields that we use to simplify the analysis. Okay, now then these two anomalies can be summarized by this equation. So the R cubed anomaly is a term in the divergence of the R current that goes like FR wedge FR, where FR is the R symmetry field, gauge field strength. And there's also a Del Burgo-Salam anomaly proportional to trace R and R wedge R, where R is the Riemann tensor. There are a lot of R's in this formula, I apologize for that. This is the first Pontryagin class of the tangent bundle. Okay? So that this anomalous conservation equation summarizes those two statements. And of course, we already discussed at great length the fact that A appears as the coefficient of the 4-dimensional Euler density, and there's also the C anomaly, which I will not write here. Okay? And just like the operators reside in a supermultiplet, their anomalous divergences also have to reside in a supermultiplet. So there's a supermultiplet of anomalies, and if you directly supersymmetrize these right-hand sides, you again reproduce the relation, the linear relation between A and these two anomaly coefficients. And this leads to a famous formula which was first written down by Anselmi and Friedman and Grisaro and Johansson in the mid-90s. So in a standard convention for the A anomaly, the formula looks like that. Okay, so this is the formula for A in terms of the 't Hooft anomalies. And as I already explained before, the 't Hooft anomalies are considerably more robust than the Weil anomalies. We can often compute them by doing considerable violence to the theory, deforming away from conformality, by flowing in from a non-conformal theory. As long as we have control of the U1R symmetry, then we have access to its 't Hooft anomalies, and the moment we can compute those, we can compute A at the fixed point. So this dramatically improved the computability situation, and this formula allowed people to check the A-theorem in many, many non-trivial supersymmetric RG flows long before Komorowski and Schwimmer came up with an unperturbed proof. Okay? Good, so now that I've sort of 35 minutes left or so, I'm going to graduate to 6 dimensions. And the question is, what's going on in 6D, and what's actually known there? And the answer is not that much. So I think I will be more or less able to summarize what's known and then say what we added. In 6 dimensions, the first thing you might try, especially in hindsight now, is to generalize the argument by Komorowski and Schwimmer. Okay? So again, you say, let's imagine I'm in the spontaneously broken case. Again, there's a non-spontaneous version, but we'll only be discussing the spontaneously broken one. So there's a dilaton. And just like I did in 4 dimensions, I'm going to first have to parametrize the most general effective action, low energy effective action for the dilaton that's consistent with non-linearly realized conformal symmetry. And this analysis was done by Alvang and collaborators. And in the analysis, it's very useful to not just discuss the dilaton in flat space, but to actually couple it to a background metric G. This is our standard trick. Then when you do that, a Weil transformation simultaneously acts on the dilaton and also on the metric. Both of them scale like that. So you can actually form a Weil invariant combination G hat, which is phi divided by the lambda phi times G. Okay. And then one thing you can very straightforwardly do is just write diff invariant local terms in G hat. And by construction, they will automatically be Weil invariant. So then if we restrict the metric back to be the flat space metric, we're guaranteed to produce terms in the effective action that are consistent with the symmetries. Okay, so that's one easy way to generate good terms. So for example, if you write the Einstein-Hilbert term for G hat, it will generate a kinetic term for phi in flat space. This is a G is a bit flat. Or more interestingly for us, if you write a term that looks like the Ricci scalar, the Ricci tensor squared, and you pass the flat space, then you'll find a term that looks very similar to the dilaton self-interaction term that we discussed in 4 dimensions, but with a different power of phi in the denominator. The different power of phi is because the dimension of the free scalar field in 6 dimensions is 2 rather than 1. Okay. Now, that's nice. However, it turns out that not all terms that are allowed can in fact be written in this form. These are the kind of manifestly violent variant terms. However, there's another interesting term you can write down. There's a term that, loosely speaking, looks like a 6th derivative term involving 6 dilatons. I'm being schematic here because there are actually very many different contractions of these derivatives, so that will not be necessary for me. And you might ask, well, okay, what is the completion of this term once I couple it to the background metric? I told you that it couldn't be written as a violent, as a manifestly violent variant term in the in the Haddad variables. Well, it turns out that if you complete this term, then you generate many kind of intermediate terms that have fewer derivatives and some powers of the metric. For example, you can get a term that looks like, I don't know, 2 derivatives of the dilaton times 2 powers of some curvature, just schematically. But if you go all the way to the end, you find that there's a term in this chain that looks like log phi times the Euler density. Okay? So it turns out that this whole object, which is kind of non-trivial to construct, has the very nice property that if you take its Weil variation, it's not 0, because if it had been 0, it would have been one of those terms, but it's precisely sigma times the Euler density. What happens here is that if you do a Weil variation, phi shifts. So this term will generate an inhomogeneous shift by E6. But unfortunately, when you vary E6 with respect to Weil, you also get some terms. And this whole other chain of terms is cooked up in order to cancel that. And what you realize when you do that is that in order to complete this chain in such a way that this simple formula is true, you are forced to add this 6 dilaton 6 derivative term that persists even when you specialize the metric to flat space. So this argument tells you that if you want such a term in the effective action, it has to come from this Euler term. And because this term shifts inhomogeneously like that, its coefficient must be delta A. Okay. The job of this term is precisely to cancel the mismatch in the A anomaly between the UV and the IR, as is typically the case for Wezzo-Mino terms. And as is typically the case for Wezzo-Mino terms, the actual matching is done by a term that is not visible in flat space. But when you complete that term, under the constraints of all the symmetries that you would like to impose, you're left with something that does survive in flat space. So the same argument is the argument that told you that the 4 derivative term in 4 dimensions have to be proportional to delta A. It's completely analogous. Okay, so we now have the most general, up to 6 derivative order, the most general dilaton effective action in 6 dimensions. Let me just write it over here to summarize. So in flat space, we have a kinetic term. We have a term that looks kind of like the term we had in 4 dimensions. But now the coefficient, which I'll call B, is not related to delta A, and in fact, its physical meaning is obscure. And then there's a very interesting term proportional to delta A, that is 6 derivative in the dilatons. And of course, they're higher derivative terms. So this B is kind of a headache. It has the interesting property of being positive, because that argument is exactly the one that told you that delta A was positive in 4D. But here it's B that's positive, not delta A. And I don't know what B means, so I'm not sure what I learned here. In fact, if you try to run some version of the 4D argument in 6D and try to prove that delta A is positive, and this is what Alvang and Friedman and collaborators did, you will find that this B always kind of contaminates whatever thing you were trying to prove is positive. So it's basically impossible to get a sharp positivity result for delta A this way. So the status of this kind of general dilaton-based approach to the A-theorem is open, and it's not been proven.
And just to be clear, so up to 6 derivative orders, there are precisely those 3 terms? There's only
Those are the only terms that survive in flat space,
Right.
and once you impose the equations of motion on the dilaton. That's a perfectly sensible thing to do here because the dilaton is physical. Again, it requires some words and some care in the case where the dilaton is kind of an off-shell background field. Good. So again, just like in 4 dimensions, we can ask, does supersymmetry help with this situation? Does supersymmetry help me say something about this dilaton effective action? And now I'm going to sort of enter the arena of supersymmetric and superconformal theories in 6 dimensions. So just a few very basic words by way of background. They come in 2 varieties. They're 1-0 theories, which are very similar to n=2 theories in 4 dimensions. They have an SU2R symmetry and 8 supercharges. And then there are the 2-0 theories, which have the same amount of supersymmetry as n=4 theories in 4 dimensions. Other superconformal algebras exist, but there are no superconformal field theories that realize them. And in fact, it can be proven that it's impossible to have local field theories with more than 2-0 supersymmetry. That's an argument that I'm happy to review after the talk if somebody's interested. Now, all known examples of interacting conformal field theories in 6 dimensions are, in fact, such supersymmetric examples. We don't know any non-trivial interacting 6D CFT unitary that is not supersymmetric. And all of these supersymmetric examples are constructed or argued to exist by embedding them in string constructions. So even in the supersymmetric case, we don't have a good handle on how to formulate them as quantum field theories. And the 2-0 theories were the first examples of these theories to be discovered more than 20 years ago, and subsequently people discovered 1-0 theories, and in fact there's a whole zoo of 1-0 theories that keeps kind of growing. You can engineer many classes, infinite classes of examples in string theory, but our understanding of them as field theories has been slow. Good. So now that we're in the regime of supersymmetric field theories, we should ask ourselves, what kind of renormalization group flows would we like to study? The A-theorem, after all, is a statement about renormalization group flows. So I should first understand what RG flows are even possible. And as I alluded to at the beginning of the talk, there are various ways you might trigger an RG flow. The possibility that we've been discussing at great length is if there's a moduli space of vacua, I can move on to that. And that's definitely something that is always possible in the supersymmetric examples because all of them have a moduli space of vacua. But the more standard thing that you might try to do is to just add a relevant operator to the action and initiate a flow that way. Okay? Now, if you are in the supersymmetric world, you might restrict yourself to the relevant operators that preserve supersymmetry. They can break conformal symmetry, but they should preserve supersymmetry. And in fact, the question of whether or not you can conceivably have such operators is one that can be answered completely abstractly using superconformal representation theory. So this is not the subject of this talk, and I will only summarize the results, but a very simple result that you can prove using unitarity bounds and superconformal representation theory is that in 6D 1-0 theories, there are no supersymmetric, relevant, or marginal deformations. By deformation, I mean a local operator that you can add to the Lagrangian in such a way that preserves supersymmetry. Okay? So these flows are just out as far as supersymmetry is concerned. There are, however, many interesting relevant operators that you could add to the action that break supersymmetry. It's not that these theories don't have any relevant operators, they just don't preserve supersymmetry. That sometimes gets misconstrued, I think. Good. And the other point I want to make, because it'll be important very shortly, is that there are plenty of interesting irrelevant supersymmetric operators that you can add to Lagrange. Okay, the statement is only about the relevant or marginal ones. And it's sort of an accident.
Could be dangerous.
If you have no relevant operators, I'm not sure that you can have a dangerously irrelevant operator.
What do you mean, dangerous?
Starts out irrelevant, but it could become relevant.
But if it's just irrelevant, then it's just irrelevant. If you don't also add simultaneously a relevant operator that could make it become relevant, then probably
it's
this
hard to say what you mean by dangerously irrelevant operator if the only flow is this business of tuning your rec, where you're rec, which is what these things have.
This will not play an important role in my story, though. Good. So the bottom line is we will analyze flows of 1,0 theories onto their moduli space of vacua. This is the class of flows that is natural in these theories. And I will talk about 1,0 theories and keep the discussion very general, and then the 2,0 theories will be a special case of that discussion. So I won't single out 2,0 theories in this talk, even though you can say much more about them using the enhanced supersymmetry. Okay, and what I'm going to try and do is something very old-fashioned. I'm going to just try and consider the flow onto the moduli space and consider the effective action of the light fields on the moduli space and try to get some mileage out of the 't Hooft anomaly matching. Importantly, not just for the conformal symmetry, but also for the various other symmetries that are present in 1,0 theories. And as I said, all 1,0 theories necessarily have an SU2R symmetry. So therefore, you have a rich structure of possible 't Hooft anomalies. And the 't Hooft anomalies are conveniently encoded in an anomaly 8 form. And then you can, by the standard descent procedure, figure out what they imply for the anomalous conservation laws. And the anomaly 8 form has 4 coefficients that involve the R symmetry or the stress tensor. There's a coefficient alpha, times the second Chern class of the R symmetry squared. That's a pure R symmetry anomaly. There's a mixed anomaly beta involving both the R symmetry and the first Pontryagin class of the tangent bundle. So this is a mixed R gravitational anomaly. And then there are 2 gravitational anomalies. Purely gravitational anomalies. One of them is the first Pontryagin class squared, so it's reducible. The other one is irreducible, the second Pontryagin class. There are 4  't Hooft anomalies in 1,0 theories. And if you remember, there are also 4 Weil anomalies in 1,0 in all 60 CFTs. So again, there's a nice possibility for having a linear relation between the Weil anomalies and the 't Hooft anomalies. And this is something that I think many people suspected and expected for a long time, but it was hard to make precise. And the reason it's hard to make precise is just more or less technical. If you write the analogous anomalous conservation laws that follow from this anomaly 8 form, just like we did in 4 dimensions, you'll get something like, for example, the derivative of the R card involves alpha times FR cubed and beta times FR R squared and so forth. So this is an expression that's cubic in the curvatures rather than quadratic. It's quadratic in 4 dimensions. So the multiplet of anomalies involves a cubic curvature invariant, and somebody needs to go and supersymmetrize that cubic curvature invariant in 1,0 off-shell supergravity. And that somebody isn't me, and apparently nobody else wants to do it either. So we've been trying to do this explicitly for a long time, and a sort of direct assault is just very, very cumbersome. And so what I'm going to explain in the next couple of minutes is how to cut this problem, roughly speaking, in half, and turn it from a curvature cube problem into a curvature square problem, which not only can be solved, but already has been solved. Okay, and that will basically be the strategy that we follow. And the strategy will end up being some sort of mashup of the strategy that people pursued in 4D, where they could just supersymmetrize these anomaly multiplets, and this dilettante-based approach, which is a little more recent. So what we're going to do is we're going to study our G flows onto the moduli space of vacua. And in 1,0 theories, there are 2 different types of moduli spaces, actually 3. They're Higgs branches, just like in n equals 2 in 4 dimensions. They're tensor branches. These are the analog of Coulomb branches in 4 dimensions. but the scalars that parameterize the tensor branch live in a 1-0 tensor multiplet together with a two-form gauge field. And then there can also be mixed branches. I will focus on the tensor branch because it has the interesting property that all of the symmetries are unbroken there. So the SU2R symmetry is unbroken, and the diffeomorphisms are also unbroken. So all the 't Hooft anomalies just have to match. And the reason that none of the symmetries are broken, as I said, is that the dilaton, which is one of the scalars parametrizing the moduli space, is in the multiplet together with some fermions and a self-dual two-form gauge field such that H is star H, which is the field strength of this guy. And because it includes a gauge field, this multiplet cannot be charged under any global symmetries. Therefore, this VEV doesn't break any of them. And this guy also doesn't carry R symmetry indices, so that's a very good situation. Good. So let us now understand what we can say if we use the fact that the dilaton phi is now the bottom component of a 1-0 tensor multiplet. Well, what we can do, or what we should do, is to try to supersymmetrize this action. Okay, we have to now try to understand how to supersymmetrically complete these terms, the one with B and the one with delta A. Okay, so the two derivative terms are trivial. At the two derivative level, this is just the free theory, so box phi is 0, and this equation has superpartners, E slash psi is 0, and also dH is E star H is 0. That's just the free abelian tensor multiplet, so that's not very hard. And then, in order to understand how to supersymmetrize the higher derivative operators, we will interpret the higher derivative operators as irrelevant supersymmetric deformations of the leading two derivative theory. And this is the point in the analysis where we can utilize our understanding of the classification of supersymmetric deformations that comes from representation theory. I'll not go through the argument here, but I'll just state the relevant result for the case of tensor multiplets. And the consequence of this analysis is that the only SUSY deformation in a theory of a free abelian tensor multiplet, a single free abelian tensor multiplet, is of the form q to the 8th times O. So it's a full D term. There are 8 q's in the theory in total. And O is a Lorentz scalar. Okay. It should have the property that it's not a total derivative. Because if it is a total derivative, that derivative just comes out, and this thing will be a trivial deformation of the action. And if we are on the tensor branch, we should make sure that the SU2R symmetry is unbroken. So the third requirement is that O is an SU2R singlet. Okay. So this is very, very straightforward. And now we're just going to try to write candidate operators O and see if we can match the 4 derivative and 6 derivative terms in this effective action. Okay. The 4 derivative terms are easy to match. Let me remind you how you count derivatives in supersymmetric theories. Scalars don't count because we're in the moduli space. They have weight 0. Fermions and supercharges have weight 1/2, and derivatives and H fields have weight 1. Okay, so this q to the 8th already has the same weight as 4 derivatives. Therefore, in order to produce this 4 derivative term, I just need to stick something of weight 0 in there. Okay, so the 4 derivative term can be supersymmetrized by writing q to the 8th on phi to the 4th. It has 4 fields and 4 derivatives. No problem. And in fact, there's an infinite number of terms like that that you can get by expanding the denominator here in this formula. That turns this non-local action into a local one if you expand the fluctuations. And now let's try to do the same exercise for the 6th derivative term. Okay, since the q to the 8th already has the same weight as 4 derivatives, now my operator O should just have weight 2. So in order to get the 6th derivative term, I'm going to try to write q to the 8th on O, where now this scales like 2 derivatives. Okay? And now there's a very simple process of elimination that you can do, where you just try to write all the possible local O's that has weight 2, is a SU2R singlet, a Lorentz scalar, and a total derivative. Okay, this is a simple exercise. There are 5 or 6 possibilities that you can try out. And it turns out that none of them satisfy all requirements simultaneously. Okay, so such an O does not exist. I'm happy to go through an example if this is of interest to people, but I'm also happy to just state the answer because it's extremely explicit. You know, you try all the possible combinations. There are maybe order 6 or 7 of them, and all of them violate one of these principles. They're either not Lorentz invariant, or not SU2R symmetry singlets, or in the simplest case, they're a total derivative. For example, the simplest thing you might try, maybe I'll just write that. The simplest thing you could try is something that's a power of 5 times e phi squared. But that thing is actually a total derivative up to a term proportional to box phi. So you can use the leading order equations of motion to pull out a derivative, and then this term is true. Okay, so that's interesting. So we have the conclusion that this term cannot be directly supersymmetrized on the tensor branch of 1,0 theories. That basically sounds like a contradiction, because we need this term in order to match the A anomaly between the UV and the IR theories. Okay? But there's a way out. The way out is that, as frequently happens when you work with moduli space effective actions in supersymmetry, when we checked that this 4 derivative action was in fact supersymmetric, in other words, when we used the fact that this operator is annihilated by all the Q's, we used the leading order equations of motion for phi. Okay? So that means that this thing is actually not supersymmetric at higher order, and instead you need to modify both the supersymmetry transformations and the effective action order by order in the derivative expansion. And this process can generate 6 derivative terms and higher derivative terms. But because it is a second order effect, this immediately proves that delta A must be proportional to B squared. Okay? Because the way that you generate 6 derivative terms is by varying this term, which is linear in B, with respect to the modified supersymmetric transformations, which are also proportional to B. So this is a standard argument, and it immediately shows that delta A has to be proportional to B squared with a coefficient here. Let me not write it as squared, let me write some coefficient here and emphasize that that coefficient is completely model independent. It is just fixed by supersymmetry.
Well, why did you say the modified supersymmetry transformations were also proportional to B?
Well, because if I didn't add this term to begin with, I wouldn't have to modify the supersymmetry transformation.
I came from that.
Yeah.
Okay, I'm sorry.
So you add that term, it's order B, then it induces an order B transformation, and then the combined effect is order B squared. Good. And in some units, which I like, you know, there are various standard units for how to normalize the A anomaly. There's a nice set of units for supersymmetric theories where you take the single 2-0 tensor multiplet and you assign it A equals to 1. In those units, this coefficient is horrible. It's like 98,000 pi cubed or something. So let me not write it. But the important thing is it's model independent and it's positive. Okay? So this equation, which follows only from supersymmetry, immediately implies that delta A is positive. Because it's trivialized the positivity of A. It's just a perfect square of a quantity that couldn't be 0 in an interacting theory. Okay, so this is the proof of the 1,0 a-Theorem for flows onto the tensor branch. And it's come about in a very simple way by arguing that the constraints of supersymmetry on this effective action just imply that delta A is quadratic in B. Good. So in the last 10 minutes or so, I want to now explain how I can leverage this understanding in order to actually write down a formula for A in terms of the 't Hooft anomaly coefficients. Because essentially what's happened now is that I have reduced the problem of studying delta A from a 6 derivative term to a 4 derivative term, or in the language of curvatures, from a 3 curvature term to a 2 curvature term. So I've kind of gained 1 order of magnitude. Okay. Now this 4 derivative term is still a D term. It's q to the 8th on something. So it might sound ambitious to say anything about it, But the reason we're going to be able to say something is because it turns out to be related to anomalies. And in fact, there's a very similar old story by Nadi Cyberk and Michael Dine, where they were also able to constrain certain d terms in 4D n equals to 2 theories by relating them to anomalies. It doesn't work for any d term. It's a special d term that's associated with the dilaton and the conformal anomalies and so forth. Good. So in order to understand how the 't Hooft anomalies come into the game, let us remember that there are no symmetries broken on the tensor branch. So you might naively think that the change in the anomaly polynomial between the UV theory and the IR theory of the tensor branch is just 0. Because there are no Goldstone bosons in the infrared to absorb any potential anomaly mismatch. However, this is wrong in 6 dimensions. In 6 dimensions, it turns out you can match certain anomalies even in the absence of spontaneous symmetry breaking. And the reason for that is that there is a 6D Wien-Schwarz mechanism, which involves the self-dual tensor field. Okay, so let me quickly say how this works. We know that the tensor multiplet has this B field in it, and we could contemplate writing a term in the action that's of the form B wedge x4, where x4 is some 4 form. So this looks like a either electric or magnetic source for B, depending on which way you like to interpret it. But in fact, since B is self-dual, it's an electric and a magnetic source. And this type of self-dual electromagnetic source actually leads to an anomaly. The coupling of a self-dual 2-form to a source like that is actually anomalous. And if you add a term like that to the action, then you can generate a contribution to the anomaly 8-form that's quadratic in X. Okay? This is a 4-form. The anomaly polynomial is an 8-form, so this formula makes sense. That means that as long as the mismatch in the anomaly has this factorized perfect square form, it can be matched by including in the low energy theory such a term. There's a pesky factor of a half here, which comes from self-duality, which is pretty hard to get straight, but it's standard. So in our case, what kind of 4 forms do we have in the game? Well, we have one 4 form which is proportional to the second Chern class of the R symmetry gauge field with some coefficient little x. And then we have the first contrarian class of the tangent bundle with coefficient little y. Okay? And if we then include this term in the interaction and expand out this perfect square, then this will generate a quadratic, kind of bilinear quadratic contribution to the alpha, beta, and gamma coefficients in the anomaly polynomial. So delta alpha will be proportional to x squared, delta beta will be proportional to 2xy, delta gamma will be proportional to y squared. Okay, so we have now on the board 2 different anomalies that are quadratically related to things that appear at 4 derivative order. A is b squared, and delta alpha, delta beta, delta gamma are quadratic in x and y. So therefore, they should be related by supersymmetry. Right? These terms also occur, morally speaking, at the same order in the derivative expansion. If you try to actually figure out what order this term should be, it turns out that it's the same order in this term. Okay? But the important technical improvement now is that we've reduced the derivative order by 1. Okay. So now we're sort of at the end of the tightrope, and we need to actually supersymmetrize these 4 derivative terms in the presence of background fields. The reason we need to do it in the presence of background fields is because this term vanishes in flat space. Because x4 is a function of the background gravity and R symmetry fields. This is still a hard problem, but fortunately it has been solved in a very beautiful paper by Salam and Sezgin and Bergshoff, which is, I think, older than I am, and older than Carney's conjecture, and sort of lay dormant for a long time, but they were interested in the mid-80s in curvature squared correction to 6-dimensional supergravity. And it turns out that they exactly supersymmetrized the term that we're interested in. And they wrote it up in a way that is perfectly intelligible, even to non-supergravity enthusiasts. So if you just look at their answers, you can immediately read off the relation between the B coefficient here and these x and y coefficients that appear in this coupling. Okay. You can literally just lift the answer from their paper. And if you do that, you find that there's some nice formula B is a half exponential. Okay? So now with the totality of formulas on the board, we'll be able to write a formula for delta A in terms of delta alpha, delta beta, and delta gamma. Right? You just plug B into here, then you get something that looks like x squared minus 2xy plus y squared. And that you can substitute with alphas, betas, and gammas. The only thing you need to be careful about is to write out all the prefactors that I've been sort of suppressing for simplicity. So if you replace squiggles with equal signs, you get a 16/7 delta alpha minus delta beta plus delta gamma.
Do you understand why B is positive then?
No, it's actually not. It's actually the other way around. You should choose x and y in such a way that b comes out positive. X and y, the sign of x and y is not fixed by the Green-Schwarz mechanism because these are quadratic relations. So x.
But in the effective action, you cannot
B
look
should-
at that action and see that x and y, x has to be larger than y.
No, it's very not obvious. But you can't look at this effective action either and tell me that b is positive. It requires some non-trivial physics. It's not manifestly positive. Good. So okay. So this is a formula for delta A. Of course, we already proved that delta A is positive, but the virtue of this formula is now that it relates the change in the Weil anomaly to the change in the Hooft anomalies, and it's very easy now to integrate it and to give a formula for A itself. And this is going to be the last thing I'm going to say. So clearly, the only way to integrate these terms is like that. That's trivial. But there's also a fourth Hooft anomaly coefficient, delta, that turned out not to flow. The reason it doesn't flow is because it's an irreducible gravitational anomaly, so in fact it has to just be exactly the same in the UV and the IR, and our formula for delta A cannot possibly pick it up. So there's an unknown coefficient here that I haven't fixed, and that I don't know how to fix. But now I can just plug in one example. Right? For example, take the free 1-0 hypermultiplet, where it's easy to compute the left-hand side and the right-hand side, and then you just fix the number to be 6/7. So we only needed to fit a single number. And I emphasize again, this number is derivable if you were valiant enough to actually supersymmetrize the full anomaly multiplet. Then you would have access to it.
It's universal.
It's universal, totally model independent. But in order to really prove that, I think down to the wire, you would need to do the harder exercise of supersymmetrizing the anomaly multiplet. Okay, so this is the formula that we've been hunting for. It's the analog of the Anselmi et al. Formula in 4 dimensions, and now we can go wild and compute the A anomaly for any theory, any 1-0 theory that you know the Hooft anomalies for. So for example, you can go ahead and compute the A anomaly for the 2-0 theories. The Hooft anomalies for the 2-0 theories were computed a long time ago by Harvey, Minasian, and Moore by looking at anomaly inflow into M theory 5 branes. So alpha, beta, gamma, delta are known for these theories. And if you just stick them in, you'll find a formula for A that looks like this. Here G, little g, is an ADE Lie algebra, which characterizes the 2-0 theories. H check is the dual Coxeter number, D is the dimension, and R is the rank. And this is an exact formula for the A anomaly of all 2-0 theories in all the 1/n corrections and so forth. This is it. This is the full answer. Now, we had actually computed this answer a little earlier this year in a paper that Clay and I wrote with Shi Yin by reducing the 2-0 theories on a circle and relating this computation to a perturbative computation in 5D Yang-Mills. The reason that you can do that for the 2-0 theories is because the maximal supersymmetry implies very strong non-renormalization conditions that allows you to track this computation from the 6D to the 5D regime. So that's a very special thing that you can do in 2-0 theories. So this answer had been computed a little earlier this year, but now we can reproduce it from this anomaly matching argument, and that's a very non-trivial consistency check of the whole story, that this formula is actually correct. And now you can look at your favorite 1-0 theory, the theory of small E8 instantons, or branes on an orbifold, or whatever. There's a whole infinite zoo out there, and many of their anomaly polynomials are known. And now you can compute A. And we proved that the A-Theorem holds for tensor branch flows, but we didn't have an argument for Higgs branch flows. I didn't have time to explain why we didn't have an argument for Higgs branch flows, but we don't. Nevertheless, now that you can compute A explicitly in many examples, you can actually check whether the A-theorem also holds in Higgs branch flows, and indeed, in all of the examples that have been checked, it does. There's a lot of stuff that's left to do and that's left to be understood, but I think this is a natural stopping point for me. Thanks.
Say something about the overall positivity or non-positivity of A?
Yeah, good. So that's the thing that I would have talked about if I had 10 more minutes. So you just gave me you just gave me more time. Thanks for that. So indeed, it is not obvious from anything that I've said whether the A quantity defined by this formula is actually positive. Now you might think it's kind of obvious because I've proved that delta A is positive along the flow, and then all you're left with is the free theory on the tensor branch. That's a theory of free fields. So first of all, you should be able to compute its A, and secondly, how could it not be positive? The way, the thing that throws a wrench into this argument is the following issue. So the A anomaly of a hypermultiplet or a tensor multiplet is positive, and the reason is that these are actually free conformally invariant fields. But the vast majority of interesting 1-0 theories have abelian or non-abelian gauge fields on the tensor branch. Okay? Now, a gauge field is not a conformal field theory in any dimension other than 4. So it is far from obvious how you would assign a sensible value of A to even a free abelian gauge field. Now, this starts sounding very confusing because we started with a conformal field theory and we went onto the moduli space, so conformal symmetry was only broken spontaneously, so how could I end up with something that's not a conformal field theory? The way this comes about is that the Maxwell kinetic term is always multiplied by power of the dilaton in such a way that the combined dilaton gauge system is actually conformally invariant. So this thing, if you look at the dilaton plus this, it actually has a traceless stress tensor. And the reason is that the dilaton does the job it's designed to do. It's a compensator for conformal transformations. However, if you fix a VEV for phi, and then you flow to the deep, deep, deep infrared, then you might worry that these things effectively decouple up to maybe some dilaton zero mode or something. And therefore, again, you're kind of faced with the problem of, how do I write down a number for the infrared value of the A anomaly when my theory includes this? And as I said, this is not a problem you can kind of wish away by saying, well, let's not study these flows, because the vast majority of interesting 1-0 flows actually produce these things. So the thing that we did, and that I think is the only thing that's consistent with superconformal symmetry, is to use this formula to determine what kind of value you should assign for A for the free vector multiplet. This formula is forced on you by supersymmetry and superconformal symmetry. So if you want AUV to be equal to AIR plus delta A, with all the pieces exactly as we said, I think this is basically a requirement. But if you plug in the values from the alpha, beta, gamma, and delta coefficients for the free vector multiplet, you get an annoying number. Not just an annoying fraction, it also has a minus sign. Okay? So you get a negative contribution to the A anomaly. And it's not completely clear to me at this stage what the interpretation is. It might make you worry that you could have a situation where if you have a theory with many, many gauge fields in the infrared, then the negativity of those infrared values could overwhelm the positivity of delta A and lead to a negative A in the UV. That never seems to happen. There seems to be some non-trivial consistency condition on these theories that says that delta A is always big enough to overwhelm whatever negative value you got in the IR from gauge fields. And we checked that in several examples. However, I think the physical interpretation of this is still a bit unclear. My attitude now is that this number is forced on you by consistent superconformal bookkeeping. However, I would be reluctant to say or claim that this is a sensible definition of the A anomaly for a free Maxwell field in 6 dimensions, because I don't think that that thing is, strictly speaking, well defined. The trace of the stress tensor is a non-zero operator. It's not a conformal field theory. This is something that we're definitely trying to understand better. I suspect that if you carefully take into account the coupling to the dilaton in this vector tensor system, whose role in life is to guarantee that the stress tensor is actually traceless, you can do a sensible computation that will hopefully give this answer. But right now, this answer is just forced on us by anomaly matching, and I'd say a crisp physical interpretation is still missing.
What rides on positivity or there being an A function, which?
Well, there's no a priori guarantee that A will be positive in a unitary theory. However, it turned out to be so in 2 and 4 dimensions, and the interpretation as counting degrees of freedom kind of goes out the window once you allow negative A. So I don't think it's not logically necessary for the validity of the a-Theorem, since that's only a statement about delta A. But it is a nice kind of co-property that jives well with what we expect.
And a Hoffman-Maldacena type argument?
Very good. So the Hoffman-Maldacena argument is about the 3-point function.
Right.
And in 6th dimension, the 3-point function only knows about the C anomalies, but not about A. A first appears in the 4-point function. So the Hoffman-Maldacena type argument by itself doesn't tell you anything about A.
This calculation, you say that Osborne did in 4D can be done in 6D, like conformal perturbation theory?
Ah, good. So you're asking, can one generalize the conformal perturbation theory story to 6D? I have 2 comments about that. First of all, if you try to do it straightforwardly, just in a non-supersymmetric theory, you immediately run into problems. The Osborne argument does not generalize. And there were various papers by Osborne and Sturgeon and collaborators that analyzed that. The second comment, which is more of a philosophical one, is that I don't know any interesting interacting CFT that can be described by conformal perturbation theory around a bosonic fixed point. All these theories are supersymmetric and they're isolated. They don't have any couplings or anything that you could analyze in perturbation theory. So even if one were able to do such an exercise, it's not clear what it would mean or what it would tell you about these theories.
And you could perturb them with a non-supersymmetric
You could.
operator and say
The only
how-
problem with that is that the only non-supersymmetric operators are like very relevant. They're not kind of, they don't have dimension 6 minus epsilon. They have like dimension 4 or something, or 3. So you'll be initiating a very rapid RG flow. So it's conceivable that conformal perturbation theory will break down very quickly. That's just because these operators sit in short multiples of supersymmetry, which are kind of fixed integer dimensions. You cannot tune the dimensions to be arbitrarily close to 6.
Well, if there are no other questions,
Thanks.